All right, welcome everyone. Good afternoon. This is week 10 of our biochemically review, so we're very near the end of the semester and also very near the third exam. So this is also the point in the semester where I kind of stop asking a bunch of questions because there's not a ton of calculations to do. Actually, there's very few. And so at this point, this is where I start talking concepts and we start spending a lot of time kind of very similar to your slides. And in some cases, I do take pretty much entire slides out of your PowerPoints and want to talk about those. So today we're going to be talking about glycolysis in pretty much as much depth as we possibly can. I believe you either just covered the first phase of glycolysis and you'll cover the second phase tomorrow, or you're covering the first phase tomorrow and the second phase next Tuesday. But either way, this is a really good way to just keep yourselves prepared for it. So I know last week we covered the basic reactions in a bit of depth. Not really depth, but really just kind of went over them individually. Today we're going to do the same. We're going to add things like energy, things like inhibition, and some of the weirder stuff to it. And yeah, I hope that helps. So we're just going to go ahead and get started. So it's important to understand the two phases of glycolysis are split not because it's convenient, although it is convenient, but because of the purpose of each phase. So the purpose of phase one is right here, right? You want to prime the reactions, okay? And what that means is we're putting energy in to get more energy out, right? So as you guys can see right here, we're using 2 ATP, and then over here, we're getting out 4 ATP and NADH, okay? And so priming the reactions means we're putting in some work now so that we get a lot more out of it, right? And so that's why the first phase is called the priming phase, or the priming reactions. And it's because it's the phase that prepares your glucose to be converted into eventually energy, okay? The second phase is the one that actually gives you energy. So this is where you get a net gain of energy, or like we talked about when we first discussed oxidation reduction with NADH, it's reducing potential. So it's effectively potential energy. So I'm just going to put potential here as well. And at some point in the semester, I believe next week, it might be the week after though, we'll start talking about kind of the math behind reduction. Actually, I think it's a little bit later than I expected. I think it's week 13, not week 12. Okay, so we start with glucose. Not super important, but I like to mention it. It is D-glucose. And so thinking back to our carbohydrate unit last week, D-glucose is a glucose that has its fifth alcohol from the carbonyl, or like if the numbering from the carbonyl being number 1, so in this case the aldehyde, the fifth alcohol has its OH group to the right. That makes it D-glucose, okay? And we see here that this reaction uses ATP. So this is one of those priming reactions, okay? Because it uses ATP to give us glucose 6-phosphate, okay? Now there are 2 enzymes for this reaction, and I very quickly glossed over most of the enzymes last week. This week I'd like to actually talk about those enzymes. So hexokinase and glucokinase are the 2 enzymes that both catalyze this reaction, but they do so for different reasons, and they do so in different places. So glucokinase is only present in the liver. Hexokinase is present pretty much everywhere in your body that is going to do glycolysis. So for the purposes of this class, I'm basically going to say muscles, because that's where most of glycolysis is being done to give your muscles energy, okay? But I do mean pretty much everywhere. So why are they different? And the reason that they're different, and we're going to talk in more depth about affinities for each of them and all that stuff once we've covered this. But before we do, I just want to mention glucokinase is the enzyme that, since it's in the liver, it's what starts off glycogenesis, okay? All right, and what glycogenesis is just a quick introduction to it. We're going to learn it in more depth later. Glycogenesis is exactly what it sounds like. It's the genesis or the creation of glycogen, right? So that occurs in the liver, and that's why it has a specific enzyme for it. Again, we're going to go in a bit more depth about it later. I just wanted to introduce that topic, okay? All right, so now we have glucose 6-phosphate, okay? And one thing before we get into this next reaction is from glucose to glucose 6-phosphate, it's important to note that, so this is using ATP to phosphorylate. if we were to use, for example, we use one down below, let me think. Right here. So we phosphorylate. Actually, I'll get there when I get there. I don't want to go too far ahead. Okay. So, right, so this uses ATP hydrolysis to add the phosphate group. Let's think about that for a moment. I told you all, gosh, it must have been week 5 or week 6, that ATP hydrolysis has a delta G naught prime of somewhere around negative 30.5 kilojoules per mole. Okay? No matter how non-spontaneous the substrate level phosphorylation, which would be just inorganic phosphate plus this glucose gives us glucose 6-phosphate, by coupling it to ATP hydrolysis, we make this reaction very, very spontaneous. Okay, so very spontaneous. Okay, so why is spontaneity important? And this is something that I think is kind of, we're bringing all of the subjects together, and it can be a little bit confusing why we're doing that when it's a completely separate subject. And the reason that we bring spontaneity into this, the reason that you guys had to cover it in, must have been week 3 or something, is because spontaneity governs whether this will obviously happen, right? If it's spontaneous, it'll happen. If it's non-spontaneous, it won't happen. So in our body, glucose, ATP, these things are worth their weight in gold, more than that even, because they're the energy that we need in order to survive, in order to breathe, in order to do anything. And so, excuse me, and so we need to understand whether a reaction will happen, won't happen, or under which conditions it will happen. Because the conditions allow us to, for example, marathon runners can run marathons because they train in a certain way to make sure that they're able to maximize the amount of work, basically, they'll be able to do with the amount of oxygen they have. So that's why we care a lot about the energy and the delta G values. And once I finish going through glycolysis again, you'll see the delta G values, and I'll show you kind of the significance of it all. Okay, so the next reaction is an isomerase reaction. Okay, and I'm just going to highlight the part of the enzyme that I care about. So an isomerase, I remember, just moves something around, basically. And in this case, we convert our pyranose ring, I apologize, I misspelled it, pyranose ring, to a furanose. Furanose, excuse me, right? So given that we go from pyranose to furanose, given that we go from glucose to fructose, we're not actually changing anything. And that's something that I think is really weird to a lot of people is, yes, this is happening. Yes, this is, a reaction, but the amount of carbons, hydrogens, oxygens, phosphates, the amount of every element is staying the same. And so this doesn't take a ton of energy. It's just a rearrangement. Okay? However, this reaction is important for another reason, and I'm going to put a star on it, and we'll come back to it later. Okay? We'll come back to it when we get to the question about it, I should say. All right. So that was reaction number 2. Reaction number 3, this is the part that should have a star, I apologize, but it's the fructose 6-phosphate reactions. Okay? This is, once again, oxidative phosphorylation. We are using ATP to phosphorylate our, in this case, F6P, okay? And we use a kinase for that reaction, okay? So it's important to remember kinases. So we see hexokinase and glucokinase add the ATP. We saw phosphofructokinase add an ATP. When we look over to the right side, we have phosphoglycerate kinase. We have pyruvate kinase. These are all dealing with ATP, and so that's a really great way to kind of link the two. When I have ATP, when I'm using or creating ATP, I have kinase somewhere in my I have ATP somewhere in the reaction. Okay. All right. So now getting back to this reaction. So we're just adding a phosphate group, not much to it. All right. Let's move on. All right. Reaction numbers 4 and 5. And I mentioned last week we kind of pair these two because we do reaction 4 and we get 2 products. So reaction 4, the aldolase, so an aldol cleavage, that's fine. I mean, not much special about that reaction. It's fine. Gives us dihydroxyacetone phosphate, and it gives us glyceraldehyde 3-phosphate. Now these two are important in their own ways, and they're both, like, both of them can do things, but for glycolysis, we assume that this reaction 5 happens completely to the right, okay? So they draw equilibrium arrows because these two are in equilibrium, And once again, this is an isomerase, just to point that out. So we're just changing the structure of these. We're not adding or removing any elements. So what we like to do is we say this aldolase cleavage reaction is going to split into product A, which we don't care about, and product B, which we do care about. And then we're going to convert all of product A into product B. So now we have 2 product B. Okay, that's exactly what we see here. From now on, the right side, so phase 2, is going to be 2 of everything because we're assuming we have 2 glyceraldehyde 3-phosphate. Does it work this way in real life is a much more complicated question. I'm going to give the answer pretty much because remember that glycolysis is both a fast pathway. It doesn't take like hours and hours and hours to do glycolysis. And it's a pathway that's almost always happening. So when I move my muscles, I need energy. I might be using glycolysis right then and there. And so because of that, this glyceraldehyde 3-phosphate is being used very quickly. It's always being depleted. And so this DHAP is based on Le Chatelier's principle, like we learned in Gen Chem and we used for the MWC model, is being converted into G3P, and this equilibrium is to the right, okay? So from now on, like I said, we're going to be talking 2 of everything, okay? And the first glyceraldehyde 3-phosphate reaction is one of the reactions that I really wanted to point out as being substrate level phosphorylation, okay? So now you guys see here, we're using an inorganic phosphate to phosphorylate our G3P, okay? So this usually is going to take a lot of energy. The NADH, NAD plus kind of thing is helping us with that energy, okay? So this reaction, not too much special about it once again. It's just a reaction there. It's just really important to recognize this is the only substrate level phosphorylation in glycolysis, okay? Glycolysis, okay? So this is the point where, this is the only time we actually use inorganic phosphate, okay? All right, so now reaction number 7. Reaction number 7 takes our 1,3-bisphosphoglycerate and using glycerate kinase removes 1 ATP, right? There's 2 ATP. Just a reminder, we have 2 glyceraldehyde 3-phosphate. So therefore we have 2 of our 1,3-BPG. And therefore this reaction happens twice, each of them removing 1 ATP, okay? Reaction 7 also gets a star. Why does reaction 7 get a star? Because this is our break-even point, okay? We invested 2 ATP to prime our glucose in phase 1. And now we've broken even. We made back those 2 ATP, and we actually got something out of it. We got NADH, which, like I told you guys, gives us that reducing power, okay? So at this point, glucose is kind of paid off, okay? Everything after this is kind of bonus. So reaction 8 with now 3 PG or 3-phosphoglycerate. We've removed 1 phosphate group to give ATP that phosphate. And we're left with this 3 PG. 3 PG using a mutase, which is, I believe there's a very specific difference between mutases and isomerases, but I'm afraid I don't remember it. For the purposes of this class, it's a variation of an isomerase reaction, okay? And so we see this phosphate group moves from the 3rd position to the 2nd, and we're left with 2 PG, okay? Right? Enolase, so reaction 9 is a really weird reaction that we're going to come to later, and we're going to talk about it in a lot more depth later, okay? But reaction 9 is also an interesting reaction for 2 reasons. The first is, and I talked about this briefly last week, I didn't talk about it this week at all. We see magnesium here. And there it is, magnesium here. And here. So we pretty much see magnesium every time we see, every time we see a kinase, we see magnesium. This is one of those reactions that does not involve a kinase, but does involve magnesium as what's called a cofactor to our enzyme, okay? It also involves potassium. So cofactors are not super tested on. It's important to know that magnesium is a cofactor pretty much every time ATP is involved. Potassium is, I think it's important to know, but it's not as important as magnesium, okay? This enolase reaction happens to give you phosphoenol pyruvate, and then finally pyruvate kinase removes one phosphate group from it, and we're left with ATP once more and pyruvate, right? So this is where we get a net gain of ATP. So this is like profit, if we want to think of it like that, okay? We also came out with, like I mentioned, these two NADH that I have over here in green. These are also very, very useful for us. However, what I believe the most important thing is this pyruvate right here. This is, as I've called it, I think, a few times, and as your professors have probably said, the most connected metabolite. This pyruvate can go on to help make amino acids, which I'll abbreviate AA, amino acids. It can go through the electron transport chain and the tricarboxylic acid cycle to give us more energy. It can go through lactate dehydrogenase the lactate dehydrogenation reaction. It can go through a million different reactions to give us different things depending on what we need. This pyruvate is, in my opinion, the most important, one of the most important things in our body. Okay, and once again, we get two of them. I don't know if I mentioned that. I apologize if I forgot. We get two of them. Okay, why do we get two? Because we had two G3P. Each G3P gives us one. Okay, all right. So I told you all we're going to talk about the energy, and this is that energy. Okay, so this is basically saying what is the Gibbs free energy, or the delta G, of the following reactions. So this is the first step of glycolysis, which is step one was glucose to G6P, which is glucose 6-phosphate. Step two was the isomerase reaction. Step three was the fructose 6-phosphate to fructose 1,6-bisphosphate. I don't know if FBP, whatever you guys would prefer. Then we have 4, 5, 6, 7, 8, 9, 10, and then phosphoenol pyruvate to pyruvate. Okay, so why did I specifically kind of point out 1, 3, and 10? Is because 1, 3, and 10 are the spontaneous reactions. Everything else is pretty close to neutral, right? So these three highlighted steps are very spontaneous, right? And so linking back to what we talked about in the metabolism unit about how catabolism and anabolism tend to use the same enzymes for the kind of reverse pathways. So this is glycolysis if we were thinking about gluconeogenesis, which is almost to the reverse of glycolysis. Well, these highlighted steps are the steps that gluconeogenesis cannot steal. Any other step? So if we were to look at, this block of steps right here could go either in the forward direction or in the reverse, like the reverse reactions could happen. So these enzymes can be used by either glycolysis or gluconeogenesis. So without having learned gluconeogenesis at all, without having even touched the section of the book that it's in, oh, and this one is also kind of lumped in with that. Sorry, without even touching gluconeogenesis, you guys can already name 1, 2, 3, 4, 5, 6, 7 steps of gluconeogenesis right now, because they're basically the reverse of the forward reactions that we learned in glycolysis for steps 2 and 4 through 9. 1, 3, and 10 are the only weird ones where we have to do something else using a different enzyme or something else different to figure that out. Okay? So that's the free energies. Okay? The free energies are also kind of matching what we talked about before, right? The Gibbs free energy of ATP hydrolysis is -30-ish. This is -35. What does that tell us? It tells us that this reaction could happen without ATP, but it probably, but ATP really helps it a lot. This reaction could not occur without ATP. This reaction doesn't use ATP. It actually provides us with ATP, but it's spontaneous anyways. And we're going to talk about reaction 10 because it is one of the weird ones. Okay, all right. So now let's get into some of the questions. Which reactions of glycolysis under biological conditions are irreversible? So when I read under biological conditions or biochemical conditions, I'm instantly thinking we're not in delta G naught anymore. We're in delta G naught prime. Delta G naught prime. Okay. Why? Because remember, it's pH of 7. Okay, that's the difference between the two, not 1 molar. 1 molar. Okay, that's the big difference between the two, and it makes a big difference for all of these reactions. Okay, so which of them are irreversible? Let's take a look. It's exactly what I just talked to you guys about. 1, 3, and 10 are too spontaneous to go in the reverse reaction. 1, 3, 10, too spontaneous to reverse. Okay, and so we have to do something a little bit weirder for them, and don't worry, we'll get there. Okay, so what is the significance of the phosphorylation of glucose? Right, there's 3 things. There's 3 key things that I think need to be mentioned. The first is obviously, as we discussed with the entire first phase of glycolysis. There it is. It's a priming reaction, right? It's excuse me. It allows for us to get energy out of glycolysis. That's great. Okay. Second, okay, it adds a negative charge to glucose, right? And you may be wondering why that's important. We'll get there. Makes, and I'm going to abbreviate glucose G, makes it negative. And then third, allows more passive diffusion. All right, so let's think about this in terms of what's actually happening. So first, let's make sure we know where is glucose, or I should say not where is glucose found, because the glucose is everywhere. Where is glucose going to be phosphorylated, and where is glycolysis going to happen? Glycolysis happens, it's in the cytoplasm of the cell, okay? So I'm just going to draw a very, very like basic, pretty poor drawing of a cell. So here's our phospholipid bilayer. Those hydrophilic ends, these are hydrophobic, and so on and so on. You guys get the idea. It's not perfect, but it works. So this is the extracellular space, and this is the cytoplasm. Okay, there we go. So let's think about this in terms of the actual, like, what's happening. So glucose can be found here, and glucose, I'm going to make green circles. These are each glucose molecules. Glucose is too large to pass directly through the bilayer. So glucose needs a special channel to get through, okay? And we'll use that as our channel, okay? So glucose can pass through this channel, all right? So now we have no concentration gradient of glucose, right? Because glucose is going to diffuse until there's no concentration gradient. So maybe we'll have 3 on each side, okay? And I'll go ahead and erase one of these yeah, there we go. We have 3 glucose on each side, okay? So now on this side, glucose is going to get phosphorylated. And I'll draw the phosphorylation in red. Actually, we'll draw it in blue. And the reason I'll draw it in blue is because it's actually a charge as well. And so it'll be hydrophilic. Okay. So now this channel could normally take glucose into the cytoplasm or into the extracellular fluid, depending on the concentration. But what's happened is these can no longer pass through this channel. This can no longer happen because they're now charged and this channel is kept hydrophobic. Okay, so what happens is first, this negative charge keeps glucose in cytoplasm. And then, because if we were to think of this as, you know, glucose is A and phosphate is B, we've just gotten AB, which we can call C, and now our concentration of A in the cytoplasm is low. So what's going to happen? We're going to get more passive diffusion of glucose into the cytoplasm to make up for that and to keep that concentration or going down its concentration gradient, okay? So this is going to allow for passive diffusion into the cytoplasm. So let's think about this in terms of what's actually happening. And I keep saying that, but it's arguably the most important part of this chapter, right? What's actually happening is first, glucose is entering the cytoplasm, right? Let's just go kind of in order of what's happening. Glucose enters the cytoplasm. Some does, some stays out, okay? But if I need energy, I phosphorylate glucose quickly. And then, because what if I need more energy? More glucose can now enter the cell, and none of my negatively charged glucose 6-phosphate can leave the cell, okay? So put together, what these do for us is they allow us overall to keep energy in the cytoplasm, or rather to keep glucose in the cytoplasm so that we can make more energy, okay? That doesn't make sense, please say so, or come into tutoring or ask your professor, because this is a really important concept. All right, so now let's refer back to this reaction. I told you guys we're going to talk about hexokinase and glucokinase later, and this is that time. So, so I told you all, I apologize, I seem to have lost my mouse. There it is. That glucokinase is in the liver. Hexokinase is kind of everywhere else is what I said, but the reality is it's everywhere, including the liver, okay? I just didn't want to introduce nuance into a very short discussion because that would have made it a lot longer of a discussion. So we're going to talk in terms of Km, okay? So Km. Remember that low Km means high affinity and vice versa, okay? So glucokinase effectively starts the pathway, starts the glycogenesis pathway, for glucose storage. So for those of you who don't know, glucose is stored as glycogen in the liver for us. When I've eaten a ton of sugar, that's what happens to some of it, is it gets stored. And eventually it gets stored in adipose cells and it turns into fat. But it's converted into glycogen in the liver, okay? When do I want this to happen? Do I want this to happen when I have a low concentration of glucose present or when I have a high concentration of glucose present, okay? The answer to this is we want this to happen only when we have extra. I apologize, I seem to be running out of space. When we have extra glucose, all right? Because if I have very little glucose and I need it in my muscles right now, I don't want to be wasting it in the liver. I don't want to be wasting it and turning it into glycogen to be stored when I need it now. It doesn't make sense. So we only want it to happen when we have high, that's supposed to be an arrow, it's just a badly drawn one, high blood concentration of glucose. So to reflect that, glucokinase has a high Km for glucose relative to hexokinase. So Km of glucokinase, which I'm going to abbreviate GK, is significantly greater than the Km of, there we go. Sorry, I just want to make it look better. Than the Km of hexokinase, okay, or HK. Why? This eventually translates into affinity, and the way it does that is it says, okay, it's not letting me move over any further to the right. That's okay. Affinity of hexokinase for glucose is significantly greater than affinity of glucokinase for glucose, right? So the significance of this is hexokinase can convert glucose into glucose 6-phosphate for glycolysis when we have some glucose in the body. Only when we have a ton of glucose in the body will glucokinase eventually finally be activated and start converting it into glucose 6-phosphate in the liver for the sake of gluconeogenesis, or I'm sorry, not gluconeogenesis, glycogenesis. Okay? So this is controlled by insulin and it's controlled by insulin and glucagon. Sorry, I blinked on the name of that for a moment. And so that's kind of what's happening with all of that, and that's why diabetes is such a difficult condition. So in fact, diabetes is actually, I have a question about diabetes later. I'm not going to spoil it. Okay. So quick recap of this topic, because I think it's been a little while since we started it. So which enzyme catalyzing the phosphorylation of glucose has a higher affinity for the substrate? The answer to that is hexokinase, and the significance or the importance of that is because hexokinase has a higher affinity, it's going to convert glucose for the purposes of glycolysis much more readily, and a glucokinase will only convert glucose for the purposes of glycogenesis when we have a very, very high concentration of glucose. Okay? All right, so number 4, which step of glycolysis is the step in which a cell commits to metabolizing glucose? All right, so this question is an interesting question, and it's interesting for 2 reasons. The first is I'm instantly thinking, well, it's one of the spontaneous ones, right? Because eventually it's just too spontaneous, you don't want to go backwards. So is it the first reaction? Well, I just told you guys the first reaction, we can either turn it into glucose 6-phosphate for glycolysis or for glycogenesis. So it can't be the first step because we're not committing to metabolizing glucose there. It's the third step, right? And once again, that third step is the excuse me, is the phosphofructokinase, or as I'm going to start abbreviating it from here on out, PFK. So PFK, and that's fructose, fructose 6-phosphate into, it's commonly abbreviated FBP. I'm going to say F16BP for the sake of thoroughness, so fructose 1,6 bisphosphate. Okay, there we go. Okay. So this right here is the step that commits us to metabolizing glucose rather than storing it. Okay? All right. So thinking back once again to our metabolism chapter, when you have a step like this, that this is the step where we commit. This is the big step, very spontaneous or non-spontaneous or whatever. Steps like this tend to be very, very regulated. Okay? Guess what? This one is too. It makes sense, right? And as you guys can see in the next question, number 5, let me repeat that. What substrates are involved in PFK regulation? From our discussion on enzyme regulation, what kind of regulation is this? Is it allosteric? Is it a feedback loop, etc.? Okay. So let's start off with the first one, ATP. Okay. So, excuse me. There we go. All right, there we go. All right. So I forgot to mention, this also has plus ATP, and we get plus ADP out of it. Okay. So ATP regulates PFK, right? PFK. Okay. And in fact, ATP is an inhibitor. Okay. Now it kind of like it seems unintuitive at first, right? If we have ATP, but ATP is a reactant, why would the reactant inhibit it? And the reality is, you're right and you're wrong. ATP is a reactant, but remember, we're not just looking at this reaction, we're looking at this pathway. We're looking big picture, not just a little picture. Okay? ATP is a reactant for this reaction, but we're doing this reaction to make more ATP. Okay? Sorry, I just realized that does not look very, it doesn't look distinctively like ADP. There we go. Okay? So it's an inhibitor because it is also an end goal of glycolysis. All right, So that makes it an allosteric inhibitor. Allosteric inhibitor. There we go. All right. So at a high concentration of ATP, PFK has a low affinity. Oh, wait, I'm sorry. No, let me retry that. At a high ATP concentration, the Km of PFK for fructose 6-phosphate is increased, which decreases the affinity of PFK for F1 or F6P. It decreases that affinity. Okay, and so that decreases the reaction rate, and that effectively slows down this reaction, and it stops glycolysis from committing when we already have a ton of ATP. Okay, so I like to think of them in pairs because a lot of times these inhibition activation kind of things come in pairs. And logically, the next one is AMP. Okay, and AMP is adenosine monophosphate, and it's an activator. And it's actually basically the opposite of ATP. Okay, so a high ATP concentration tells us that we have enough energy, we don't need to keep doing glycolysis. Well, a high AMP concentration tells us we need more ATP. And so it reverses basically what ATP does. It increases affinity and it decreases Km and it activates glycolysis. Okay? All right. Now it gets a little bit more complicated. So we've been talking about phosphofructokinase, and it might be more appropriate to call it PFK1. Okay? And the reason it's more important to separate that out is because there are two phosphofructokinases, right? There's the phosphofructokinase that makes F16BP, and there's the let me try that again. There's the phosphofructokinase that makes F26BP, right? So let me repeat that. We can either phosphorylate fructose 6-phosphate in position 1 and go on through glycolysis, or we can phosphorylate fructose 6-phosphate in position 2 and get an allosteric regulator, or really just a regulator of some kind, in fructose 2,6-bisphosphate. Okay, and that's the third thing on this list is F26BP. Okay, so what is it? So let's think about this in terms of what's going on. Okay, we've talked about equilibrium, or we've talked about ATP, so that's big picture. ATP says we have a ton of energy, we don't need more. AMP says we need a ton of energy, keep going glycolysis. Okay, F26BP is an activator of PFK1, of this phosphofructokinase that we talked about in question 4. Okay, so when we have a high concentration of glucose in the liver, eventually that means we get a high concentration of fructose 6-phosphate. Okay, at this high concentration, just like glucokinase, the PFK2 is activated. So at that high concentration, we make F26BP. When we have F26BP, that's telling us we have a ton of glucose, right? Or rather, we have a ton of F6P, which tells us that we have a ton of glucose kind of indirectly. And so that tells us we need to do more glycolysis because we just have too much glucose, or at least we need to commit to something because we don't need to store anymore. We have way too much of it. Let's just get some energy, right? So it's an activator. It's an activator because it indicates that we have lots of glucose. All right. So that's just about everything. Well, there's a lot more for reaction 3, don't get me wrong, but that's everything I want to talk about right now for reaction 3. We're actually going to go ahead and skip reactions 4 and 5 because they're not that important. The next reaction that we're going to talk about is reaction 6. kind of spoiled it for you guys. Which reaction in glycolysis is a redox reaction? Any reaction that uses a dehydrogenase is a redox reaction. A dehydrogenase is a kind of branch of oxidoreductases. Oxidoreductases, which tells us there's a redox reaction here. That's the first clue that we have. If it has a dehydrogenase, it's a redox reaction. The second clue we have is also highlighted in green. It's actually to the left right there. I've been calling NADH reducing potential, reducing power, right? In other words, it is a reduced byproduct that can be oxidized. So put another way, NAD plus and NADH are the oxidized and reduced forms of something respectively. So to convert from one to the other, in this case, we're reducing NAD plus to NADH, or we'd be oxidizing NADH to NAD plus, okay? So put another way, if we have one and we go to the other, we're doing redox, okay? So to answer this question, it is reaction 6 of G3P, glyceraldehyde 3-phosphate, using G3P dehydrogenase and NAD plus to NADH, and it gives us, sorry, I don't remember. Apologize, there's a lot of substrates. 1,3-BPG, okay. There we are. Okay. All right. So I've mentioned this earlier, but what is the break-even point of glycolysis with respect to ATP? I gave you guys this answer earlier, but I do think it's important to talk about. And the reason I think it's important to talk about is because let's think about it in terms of the numbers. And I think this is also kind of really confusing because the numbers themselves don't always add up, okay? So just a reminder, we use 1 ATP in reaction 1. We use 1 ATP in reaction 3. Reaction 7, which I've labeled our break-even point, we make 1 ATP, but remember, we do all of reaction 6 through 10 twice because we have 2 G3P. So this is the point, this is the break-even point, and it's reaction 7. The next question I ask is this reaction spontaneous? Let's take a look. Oh, too far. I apologize. OneNote scrolls very quickly. Okay, here we go. Reaction 7, I mean, that's the closest to 0 that I've seen. Like, I wouldn't call that spontaneous, but I wouldn't call that non-spontaneous either. All right, so let's scroll down to here and say reaction 7. Oh, I misspelled reaction. Reaction 7, and then is it spontaneous? That's the question I ask. Now, this is a question that I think is kind of confusing to some people because we're making ATP, and yet it's spontaneous, and yet it's kind of really close to 0. So that throws people off a lot. All right. So it's really weird, and that's why I wanted to mention it. Yeah, there's not a lot to say for it. It's just kind of how it is. Is that reaction spontaneous? Not really. Delta G is very, very, very close to 0. Okay, all right. Now reaction 8, and I want to say, okay, good, okay. All right, so reaction 8, let's, oh wait, no, that's number 8, not reaction 8, apologies. I think it actually might be reaction 8 too. No, it's not. Actually, hang on. So what is a condensation reaction is what we ask. The reason I scrolled all the way up here is because there's something specific I'm looking for. And that something specific, I don't know where it went. Give me one moment, I apologize. There it is. This is that something specific that I was looking for. Remember that a condensation reaction is a reaction that introduces water. Or it's, yeah, I mean, I don't like that definition, but it's basically when you're releasing water to create something, right? We can also think of it as a dehydration reaction is the reverse of this, right? Or this, I'm sorry, this is a dehydration reaction as well, because we're dehydrating phosphoglycerate by removing water from it. So condensation, what's it called? Condensation, dehydration, same thing, okay? All right, so then we're left with phosphoenol pyruvate, all right? And that's where this next question comes in. So hang on. This was reaction 9. No, reaction 8, I apologize. No, sorry, it is reaction 9, sorry. I always get those numbers mixed up. Okay, so question number 9 says, reactions 7 and 10 are both substrate level phosphorylation reactions that result in the formation of ATP. Why is reaction 10 so spontaneous and 7 is closer to neutral? Okay, so it's a good question. So let's look at this part over here. Reaction 7, like we said, is very close to neutral. Reaction 10 is very spontaneous. And yet when we look over here, reaction 7 makes ATP, uses, what's it called, magnesium, uses a kinase, okay. Reaction 10, pretty much everything is the exact same thing except there's a potassium here. Like, cool, it's not that important though, right? This is one of the very, sorry, I forgot to erase that part of my notes. This is one of the very few times that we have to look at our reactants, okay? So let me zoom out just a little bit so that we can see this entire figure, right? Because the answer to this is it's because it increases the stability of our structure. So PEP is called phosphoenol pyruvate, okay? And just a reminder for those who don't remember, this is one of the key words in that is enol, okay? You may remember it from OChem, you may not, no worries either way. And enol is exactly what it sounds like though. It's an ene plus an ol, okay? So an alkene, well, there's an alkene right here, all right, plus an ol, so an alcohol, all right? And there's the alcohol right here, basically, right? So enols are notoriously unstable, or as we kind of prefer to call it in this, high energy, okay? There's a lot of energy, really unstable, really wants to move, okay? And so when we add ATP, in other words, when we remove this, now this can now be, let me reword that. Now, this area right here in green, which was the oxygen, or which was an oxygen that could not resonate, is just a regular old tautomer. So if you guys remember from your, gosh, when was this? This must have been OChem 1, so about a year ago, I think. You would have learned about the tautomerization reactions of the enol form into the keto form, okay? The same thing happens here, okay? Because now we're able to convert this enol, this enol into the keto form. Oh, that was terrible circling. Into the keto form. This becomes very stable. So, or lower energy if that's the term you prefer to use, but they mean the same thing, okay? So let's think about this for a moment, okay? They're both substrate level phosphorylations. Makes sense. But the difference in delta G is not coming, well, it is coming obviously. This contributes to the difference in delta G, but this right here, the keto-enol tautomerization, whatever it's called, this also contributes to delta G, and we're basically saying we're going from high energy to, actually that's very poor drawing, we're going from this high energy enol form to the low energy keto form. So we're going to use some of the energy of this bond to phosphorylate ATP, and then we're going to reach stability by converting our enol back to a ketone, okay? It's a really weird concept, and it might give you flashbacks to organic chemistry, but this is why that reaction is spontaneous, whereas reaction 7 is not, okay? I hope that made sense. Once again, if it didn't, please feel free to ask any questions you may have. I'll give you guys one moment to see if there are any questions. All right, so we've talked about most of the mechanism of glycolysis. what comes next, right? We've got a lot of stuff with pyruvate, and I'm actually starting to worry I may not have enough time to answer all of this, but that's okay, we'll make it work. All right, so which substrates are involved in pyruvate kinase regulation? And once again, that same little thing. From our discussions on enzyme regulation, what kind of regulation is this? Okay, so first of all, let's ask ourselves once again, why is pyruvate kinase regulated? Pyruvate kinase is regulated for two reasons. First, it's another one of those very spontaneous steps. All right, so it's a great way, for two reasons. The first relating to glycolysis, the second not. Okay, once again, like I mentioned, it is very spontaneous, which makes it a great regulation point for glycolysis. Right? The first main reason that it's actually regulated is because if we're making pyruvate, and then gluconeogenesis is converting our pyruvate back to phosphoenolpyruvate, we're just wasting energy. We're going back and forth for nothing. Okay, so that's the first reason. The second reason is, like I mentioned before today and last week and several weeks, I'm sure, since pyruvate is so connected to other pathways, this reaction right here has to be regulated to keep track of those other pathways, okay? So we're going to talk about, it's very similar to before when we talked about PFK, in the sense that AMP inhibits, which I'm going to draw as a minus sign so that I don't have to write it all out anymore, and ATP, oh wait, I have that backwards, don't I? Yes, I do. AMP activates and ATP inhibits, excuse me, right? Because this is saying we have low energy, this is saying we have too much energy, okay? All right, now there's more, okay? Fructose 1,6-bisphosphate. So I'm going to repeat that, not 2,6 like with PFK, fructose 1,6-bisphosphate. 1,6-bisphosphate. So the one that's in glycolysis activates it. Why does it activate it? Because this is effectively reactant number 3, and pyruvate is number 10 or number 11, depending on where you start counting. Okay, I'm going to call it 10 for consistency. We want to make sure they're on the same page. So when we have high fructose 1,6-bisphosphate, we want to be making pyruvate from that. When we have low fructose 1,6-bisphosphate, we don't want to keep making pyruvate when we don't have any resources. Okay, so it helps keep phase 1 and phase 2 kind of balanced. It keeps them kind of coordinated. Okay, I don't know why it keeps making tables. Right. There's one more thing that inhibits pyruvate kinase, or one more allosteric, and that's alanine. So the amino acid we learned about earlier inhibits pyruvate kinase because alanine is made from pyruvate within one step. Okay, so if we have too much alanine, we don't want too much pyruvate, we inhibit PK, or pyruvate kinase. Okay, right. There's also a lot of other regulations. So you can have covalent modification like phosphorylation. You can have stuff like that, and it's a bit complicated. Okay, all right. So now let's talk about what's going to happen to pyruvate. Right, before I do, I want to say pyruvate is the kind of official end of glycolysis, but it's not the only end of glycolysis, and that's what we're going to see here. So this is kind of, all right, so these are our options for pyruvate. The first is it can go into the mitochondria of the cell, and then be converted to acetyl-CoA. Acetyl-CoA can go through the tricarboxylic acid cycle, or the citric acid cycle, or the Krebs cycle, whatever term you prefer for it. I use all three interchangeably. And then eventually into the electron transport chain. Okay. This is under aerobic conditions. Okay. Why? Why is it under aerobic conditions? Because the end goal of this is we use oxygen, we reduce oxygen to H2O, and in doing so, or I should say, why do we need more stuff? The reason is kind of twofold. The first is it gives us back back NAD+. So if we think of NAD+ as NAD+ is the reactant of catabolism, and then NADH is the reactant of anabolism. Reactant of anabolism. The ratio between the two kind of tells us how many catabolic reactions we're doing and how many anabolic reactions we're doing. Okay, so when we need energy, or I should say, these cycles are all great because in each of these we remake NAD+. Okay, so NAD+, and then what you don't see here is NAD+, and I'll go ahead and add that in. NAD+, okay? In all three of these, we're regenerating NAD+, right? Second, it gives us more energy to work with, right? That's the big goals of this, I guess, brown beige colored box. This first gives us back NAD+ so that we can do more glycolysis, and second gives us more energy to work with to do whatever we need to do with, right? But I'm not always working under aerobic conditions. You know, if I'm out of breath running a marathon, because I can't run a marathon, then what am I going to do? And the answer to that is these other two branches. So I'm going to very briefly talk about the middle one because I'm going to very briefly talk about the one on the right because it's not that important because it's in yeast, and then we're going to talk about the middle one, okay? So under anaerobic conditions in yeast, they go through what's called alcohol fermentation or ethanol fermentation for the goal, once again, of regenerating NAD+. We do the same, but with lactate. So the burning you feel in your muscles is lactic acid buildup from anaerobic glycolysis, if we want to call it that. This is also I don't know if it's official or unofficial. Some professors like to teach it this way, some don't, so I'm going to put it in quotes. The 11th step of glycolysis, right? And again, it's in quotes. I don't know if every professor teaches it this way. Most do, from what I know. Okay. Since this is the 11th step of glycolysis, let's go ahead and look at the pathways. Okay. So this is glucose to pyruvate. This is glucose to lactate. So the first thing I like to do to make sense of this is a big organic structure. This is a big organic structure. I don't really care about them. I know they exist, but they're not what I'm focused on right now. Okay. So, oh, by the way, the question that I pulled this, or oh goodness, what just happened? Undo whatever just happened. Don't move anything. Okay, there we go. I apologize. I don't know what caused that, but the question that is being asked here is, why would the body undergo lactic acid fermentation when the TCA cycle and ETC, or electron transport chain, give more energy? Okay. So, once again, we don't care about the organic stuff. That's cool and all, but it's not our focus right now. Okay. In both, we start with 2 ADP and 2 inorganic phosphate. And in both, we end with 2 ATP. All right, nothing changed there. That's fine. All right. Then there's the other stuff, which I'll cross out in gray. So I don't really care about the H+, I don't really care about the water. Those aren't that important to me. What is important is what's missing in the bottom one and what's present in the top one, right? I told you all we need NAD+ for more catabolism, okay? Let me be a little bit more thorough than that. If I'm running a race, I need to be doing glycolysis because glycolysis is fast and does not rely on oxygen, okay? As soon as I start running out, or as soon as I've converted all of my glucose to pyruvate, I would need to do the electron transport chain. Let's do the electron transport chain. Uh-oh, I run out of oxygen. Now what do I do? Okay. Once that's happened, I no longer have a way to regenerate NAD+ to do more glycolysis to get more energy. Okay. That's why lactic acid fermentation is necessary. It gives us back NAD+ so we can do more glycolysis quickly. Okay. So why would it? First, speed. Glycolysis is very, very fast. Second is it can occur under anaerobic conditions. conditions. Okay, those are the two key reasons that we have lactic acid fermentation, right? And that's also ties into number 11, which is about the ultimate fate of pyruvate. Is first, under aerobic conditions, TCA and ETC. Second, under anaerobic conditions, lactic acid fermentation. And third, which they don't list on here, but I think is important to mention anyways, making other things, basically. All right. We talked about alanine in the question right before this one about inhibition and regulation. We can use pyruvate to make alanine. We can use pyruvate for other amino acids, for other structures in general. Okay. All right. Number 13. Insulin decreases the concentration of glucose in the blood. How might it do this? Okay. So this question is not to ask you to understand the human body in a ton of depth or anything like that. This question is to make you guys think, how can we decrease the concentration of glucose in the blood? The first way I'm thinking of is do more glycolysis. How can we do that? So I'm thinking it gives us more of the activators or decreases the amount of inhibitors or something like that, maybe. I don't know. And these are just ideas, right? The second is maybe when we have too high a concentration of glucose, we can convert glucose to glycogen. So this is activate I apologize, I blanked on the name of the enzyme. It's very glucokinase. There we go. Right. Activate glucokinase. Something like that, right? There's also the opposite of these, right? So maybe it inhibits gluconeogenesis. Or just like with glycogenesis, it could also inhibit the opposite of glycogenesis, which is called glycogenolysis. Glycogenolysis. Okay, so I'm not saying that any of these four is correct, and ultimately the correct answer I believe ends up being the second one we listed here. The reason that I'm doing this is to kind of make you guys think, right? These are questions that could be asked on an exam, is something exactly like this, right? How does it do this? How might it do this? Is not saying know the biochemistry or know the pathway of everything that's happening in the blood. It's saying propose a logical explanation for how this can happen, right? And all four of these are logical, okay? The first two admittedly have a lot more detail because we know more about the first two. And the second one is ultimately the most reasonable because, well, the body would be doing glycolysis if it could do glycolysis, right? And so, yes, there's more and less logical answers, but this is just here to make you think. It's not here to demand a right or wrong answer, okay? All right, so now, which of the following enzymes is active first in glycolysis? This is, admittedly, if you don't know glycolysis, it's a very hard question. However, this is here to remind you, you have to memorize glycolysis for your exam. There is no way around it. You need to know every reactant, product, enzyme catalyzing it, and I would just know like magnesium is the cofactor for these reactions. I would know spontaneity and regulation. All of these you have to know on the exam, okay? So I'm going to tell you guys the way I think of it is I know this is reactions 4 and 5. This one is specifically 5 since it's the isomerase. When I see triose phosphate isomerase, I think reaction 5. I know that the phosphoglycerates are part of like 6 through 10 basically. And I know what 6 is. I know 6 is G3P dehydrogenase. I know 10 is pyruvate kinase. So I've already narrowed it down to like 7 through 9, 7 through 8 really. And that's for both of these since they have glycerates in them. So I know one is 7, one is 8. PFK, phosphofructokinase, I've done that 3 times today, is reaction 3. This one is first, okay? All right, how many molecules of ATP are produced by glycolysis? Okay, this is, in my opinion, one of the meanest questions you can be asked, because you have to be very careful about this, okay? The answer to this is 4, but 2 is also a common answer, and I would not be upset if I had put, if I had put 2 on this exam, I would feel justified in putting it. And the reason I say that is because we ultimately do make 4, that's true. However, there's a net gain of 2, okay? Now, once again, 4 is the correct answer, all right? But many people have put 2 because that's the number they memorize. And that's why I want to really point out, do not just memorize the basics of glycolysis and hope that'll work. Understand what's happening in glycolysis, okay? All right, number 16. The mechanism of triose phosphate isomerase is very similar in function to blank. Okay, so I'm trying to think of the, the triose phosphate isomerase I know does reaction 5 basically. And reaction 5 is the one that converts dihydroxyacetone phosphate to, converts dihydroxyacetone phosphate to G3P, glyceraldehyde 3 phosphate. DHAP to G3P, right? So the big things that I'm thinking of is it's an isomerase. So if I know nothing else, I can easily knock out some that have nothing to do with isomerases, right? The aldolase cleaves F16BP to those 2. So I know it's not that. They have nothing to do with each other. Phosphofructokinase and hexokinase each add phosphate groups. So I know it's not them. The only one left is the isomerase, okay? This is why your professors strongly encouraged / required that you memorize the classes of enzyme, because once you know that both of these are isomerases, that both of these fit into the same class of enzyme, even if the mechanism by which they do something is a little bit different, you know a lot about their similarities, okay? All right, and I apologize, I am going just a little bit quicker because I don't want to take up too much time because I know we need to be finished at 5:15, okay? So next question, which of the following enzymes catalyzes a reversible reaction in an equilibrium controlled step of glycolysis? Okay. This is really wordy. The things that I'm thinking of are reversible reactions, okay? I know the irreversible ones are 1, 3, and 10 are not on this list. So that's the first thing my mind goes to is, can I knock any of these choices off the list? Right, let's take a look. PFK1 it catalyzes reaction 3, so it's not this one. Wait a minute, glucokinase, just like hexokinase, catalyzes reaction 1, and pyruvate kinase catalyzes reaction 10, leaving us with aldolase. Now I want to explain the rest of this. An equilibrium controlled step, basically, it's not completely to the right, completely to the left, okay? All right, so these 2 questions, let me zoom out just a tiny bit. These 2 questions have been on exams before, and they're on an exam almost every year. I don't know if they will be because this is online, but I will say I've had questions just like this on my exam, okay? This is a great way to test if you actually understand what's going on, okay? All right, so let's talk first about the differences between the 2. And that's it. Everything else is the exact same. Anaerobic versus aerobic glucose. So I know anaerobic glucose is basically 10 steps plus lactate. And it's lactate dehydrogenase, but just lactate for convenience, okay? So in my mind, I want to eliminate everything that involves pyruvate because I know pyruvate is converted to lactate, okay? And aerobic glycolysis, I'm going to do the opposite. This stops at pyruvate. Pyruvate. So I can eliminate anything that involves lactate here, okay? Because I know lactate is not present. All right, and now we're down to, well, what actually happens? So let's think here. We get 2 moles of lactate, that doesn't help me. We get 2 moles of pyruvate, that doesn't help me. The difference between, let's do 18 first. The difference between these is, well, this one has 6 moles of ATP, this has 2 moles, and this has 2 moles, okay? The net, oh yeah, that's what we're looking for. The net is 2, and it only makes 4, so 6 came out of nowhere. So 6 is definitely wrong, okay? And it is 2 net moles of ATP, so that doesn't really help me. So the question is, does anaerobic glycolysis give us NADH? And the answer that I hope everyone remembers is no, it does not. Because remember, NADH, the point of lactate is to get rid of the NADH, making this one A. Okay? All right. Aerobic glycolysis, I sincerely apologize. This should be a 2. That is a typo. All right. So aerobic glycolysis does not regenerate our NADH. So this needs to be present, which makes D wrong and E correct. Okay. And the final question is one that I've already answered, but I'll answer it one more time because it is a very important topic that I don't want anyone to make a mistake on. What is the purpose of generating lactate from pyruvate? To regenerate NAD+ under anaerobic conditions, so we can do more glycolysis. Okay, glycolysis needs NAD+. We need to give it that NAD+ if we want energy. That's why we have to do lactic acid fermentation. Okay. All right. So that's all I have for you all today. Next week, we talk a little bit more about some of, in my opinion, the more interesting parts of glycolysis, and then also a few of the other pathways. I believe this is where we get into glycogen, but I'm not 100% sure. And then I believe your exam is also coming up very soon. So if you ever need any help, drop-in tutoring is open Monday through Thursday, 11 to 8 p.m., or Friday and Saturday from 11 to 5 p.m. Okay. Thank you all so much for joining or for watching if you're watching this on YouTube. And I hope you have a great rest of your day or night or evening or whenever it is. Bye, everyone.